Hello everyone. Today I want to explain to you about einsum in pytorch. Actually, this einsum or einsum is just one function, but I think it's quite special and quite interesting. That's why I want to put this in special video like this. But I think it will be short. And here the use of einsum. So what the use of this certain function? It's just to execute a complex matrix operation only with one instruction. And as you can see, usually in the complex neural network you will find some operation because the input is quite the dimensionality is quite high. Then of course the sum of it operation will be complex. That's why using this einsum you could write with just one line to summary several lines like 10 lines or any other else. And here some example of this einsum, and I think it will be I will just start from my previous experiment before this video. Okay, I think it will be fast if I will just show you the example. So we import torch first, and for example we have a tensor like this. It's only one dimension. So the first example here is dot operation, and to do the dot operation it's like this. The first argument or parameter in here is the most important one because it will determine how many parameters that we will need after this first parameter. So the dot operation, we must write it as string like this, or actually it it's not just I. We could use A or C or D, whatever you want, or just capital A like this. For example, we're using a capital A, and then arrow to the right and A, because oh, okay, I want to explain the arrangement of this argument here. So here we have the alphabet and comma and arrow to the right and then alphabet again. So here we have two alphabet separated by a comma like this. What the meaning of this? It means the input will be two variable. So that's why we will input A and A like this, because we want to do a dot operation A with itself. And after, and for the right arrow like this, it's same as the equal sign like this. And after that, A in here is to indicate the dimension of the output. So it just say like, okay, the dimension of the output will be same as the dimension of the input A. So the result will be like this. And as you can see here, we have a dot product. 1 times 1, 1, 2 times 2, 4, 3 times 3, 9, 4 times 4, 16. Now what if we change this? Despite the input still A, what if we change the alphabet for the second input? We will get something like this. Actually, it's the multiplication between A in here with the second argument in here is still A, but it will be a sum of this second argument. Yeah, the second parameter here, or the last parameter in here, because let's just sum this. 1 at 2, at 3, at 4, it will be 10, right? So that's why here 10 times 1, 10, 10 times 2, 20, 3 times 10, 30, 4 times 10, 40. Now let's experiment. What if this has happened? What if, okay, it will be different. It will be, for example, 5, 6, 7, 8. And as you can see here, 5 plus 6, 11 plus 7, it will be 18, plus 8, it will be 26. See, it's the sum of the second argument. So if we reverse this, it will be different. Remember, be like this. So it will be 5 times 10. All of this, all of the member in here will be multiplied by 10. That's what I mean. Okay, let's move on. Also, we could use this einsum to do the transpose. And as you know, for example, we have, okay, because we only care with the shape of the output, then let's just pound some random number, but we specify the dimension like this. For example, for the variable c here, we will get a tensor with shape 3 times 5, like this. We could easily doing a transport like this. See, we could also using einsum. AB, right arrow equal BA. Because we don't have a comma in here, so of course the input will be just one variable, and it's C. As you can see here, we're doing the transpose. And actually, we could doing outer product with this einsum. Let's just use variable A and B. Like this, so we got a two-dimensional matrix like this. And also matrix multiplication. The former one is wrong. Yeah, the former one is wrong. This is the right one. And with this incident, this is proof. This is proof that even if I mess up with the meaning of the matrix multiplication like this, the torch einsum still will follow the specification of the matching of the shape output and input strictly. Okay, it's must like this. We could also doing a batch matrix multiplication for two dimension, of course, in here. So what the meaning batch matrix multiplication? For example, we have several matrix. It's a several separate matrix, and we want to just doing a matrix multiplication of, for example, we have two beds of separate matrix here. We want to do just like one by one on one for the multiplication. Then we do it like this for the einsum. First we define the matrix. For example, the beds is 10, and then here the row is 3, 4. It's also 10. It must be 4, and here 9. No, wrong method. Okay, the output is quite long, so let's just see the shape. And as you can see here, we could output even the operation is quite complex like this using einsum. Okay, now actually you could also using einsum to do the dense layer operation. Like for example, in pytorch, usually you will do dense like this. Now for example, T in here is a dense layer, then you could using like this, and then etc. to continue the operation. Actually you could also using a einsum. So for example, in here we have S. For example, S in here is the input. Then for example, we have 128. Usually it's the size of the beds, right? And the input, for example, the parameter will be 9. And then in here we have the weight. Let's just W. And the weight in here must be 9. And for example, the dense layer in here will be outputted 5 neuron. Then it will be like this. Here S and here W. Same as before, we could do it like this. Here the shape here. Same, right? So as you can see here, I just do a dense layer operation when the input is when the input is 9 parameter, and then the dense layer in here outputted 5 dimension tensor. So here, and also actually this is just conceptual, but when you outputting something in a dense layer in the neural network, usually we will just For example, if it temporal data, so maybe plus bets, maybe yeah. If we also include bets, then your input will be have three dimension at least. It will be bet, the sequence length, yeah, the sec length, yeah, the sequence length, and the parameter like this. Actually, yeah, it you will flat this I and G in here, so it will be dense layer operation like this. So, but in here we could do that. We could do something that in ordinary dense layer can do that. So, for example, D in here. The bet is 128. The sequence, for example, 10, and then the parameter 9. And the weight will be nine. For example, output the output parameter will be 11. And as you can see here, the shape of the bed is still same and the sequence length still same. What differ is the shape of the parameter or the feature. It's because uh, we fit this D, the input D in here to imaginary the imaginary dense layer, imaginary temporal dense layer like this. And yeah, I think that's all. Yeah, it's quite simple. What I'm doing in here is just do a repetitive task to show you that all of this is possible. And yeah, see ya. Bye.